Hi again, welcome to our second video on the Permian extinction. So last time you heard about some of the environmental factors that cause the extinction, such as low oxygen levels, higher temperatures, and ocean acidification. And so now we're going to talk about how all those factors are actually connected to each other and all caused by the same thing. So the Permian extinction occurred about 251.9 million years ago at the end of the Permian period, and it was the largest of sort of the classical mass extinction events. The extinction was really severe on land and in the oceans, but like in the last video, we'll focus here on the environmental changes and the causes in the oceans. So just to recap those environmental changes, there's good evidence that the oceans got warmer and that areas of low oxygen waters expanded, and the evidence is growing that there was ocean acidification, or a decrease in ocean pH, basically. So how are those three things all connected, or are they even connected to each other? Well, there's a third source of data on this figure here, shown by the dark red points. And these are carbon isotopes, and like the others, they shift basically at the same time as the boron and the oxygen isotope records. So that suggests there might be some connection between all of these things. But maybe the carbon isotopes are not causing things. Maybe they're actually are caused by the extinction itself. So we need to look at that first. Well, we can rule that out relatively quickly for the Permian extinction because at many places, most places probably, the carbon isotope values start to change before the start of the mass extinction. And in fact, the extinction seems to occur at a point where the carbon isotopes are changing especially quickly. So that suggests that whatever was making the carbon isotopes changed had started before the extinction, and it wasn't really the extinction itself that caused the change. Although we can't rule out some kind of feedback, but the trigger was not the extinction. Right, so you've heard about isotopes before, stable isotopes. We've talked about carbon isotopes in particular before. You heard about them when we talked about the debates about some of the earliest life on Earth. But we're going to use them in a different way here, a slightly different way. So, like most chemical elements, carbon comes in more than one form or isotope. All the isotopes are carbon, but they have different weights. And you've learned before that this different weight makes different isotopes behave in different ways in chemical reactions. But for our purposes, what's really important here is that means that various types or sources of carbon end up with different amounts of carbon-12 and carbon-13 isotopes, and that will become really important. So before the extinction, the carbon isotopes in seawater had a value of about +3 or +4 units, and these units are measured in parts per thousand relative to some standard value, but the details of that aren't important for what we're doing here. But the values, we need to change them from 4, and they ultimately change over a couple 100,000 years probably to a value of 0. So that could be accomplished by, for example, adding carbon from a source with a more negative value. If it's at +4 and you add some sort of negative carbon, then the values will go down. So perhaps carbon was added from volcanoes. Volcanic carbon has a value of around -7, so that could do the job. Other possible sources, and it might come from organic matter, such as dead trees, or even like geological organic matter, such as coal. And here the values vary depending on the substance, often in the range of -25 to -30. This could be added to the system if a lot of plant matter was decaying, kind of an unusual amount, or if a lot of coal was brought to the surface of the earth and broken down or burned. In theory, carbon could come from the breakdown of limestone rock, and again, the exact composition depends on the age of the limestone rock and a variety of things, the source, but it often has values of around 0. Now, one thing that's important to note is the extinction and the carbon isotope change were geologically quite rapid. So whatever source we want, it needs to be added quickly. It needs to add a lot of carbon in a fairly short amount of time. Well, our final possible source is methane. So methane is a different molecule that contains carbon. It's often trapped in sort of underground frozen deposits, and potentially they can be released quite quickly, and methane has a very negative carbon isotope value, often around -50 or even more. So we have these different sources, and they're all lighter than +4. Some of them are very negative, and so in theory any of them could work. And in fact, it's actually kind of difficult to determine the balance of these sources, because you can get the same result by, say, adding a smaller amount of very negative methane, or you could add a larger amount of slightly negative volcanic carbon. And this can be disentangled. It requires a bunch of other data, and so it seems from all this work that the carbon that was added during the Permian extinction was mostly from volcanic with a little bit of organic matter sources. And so we'll come back to this at the very end. But actually, this is kind of a side story here. We've seen a similar, although smaller, shift in carbon isotopes in the ocean and the atmosphere today, since the 1800s, thanks to the burning of fossil fuels and the addition of that carbon to the atmosphere and ocean system. So the carbon isotope value in today's atmosphere and ocean has shifted by a bit over -1 units, as carbon dioxide has increased from about 280 parts per million to now more than 400 or 410 even. But back to the Permian extinction. What's adding all the carbon into the atmosphere then? Well, the culprit was long suspected to be these enormous volcanic eruptions called the Siberian Traps. Now, located in Russia, these are not your normal volcanoes. This is not, like one volcano is going off. Imagine something that's kind of like the flowing lava flows of Hawaii or Iceland, but covering an area nearly as big as the United States, with maybe half a mile, or a mile thick of lava. So these types of eruptions are called flood basalts, and fortunately they're really rare events. Even geologically speaking, they're very rare, because when they do happen, you get these enormous volcanic eruptions that are often caused by sort of continents breaking apart. They do tend to cause pretty severe environmental disruption, as you'll see in the remainder of this video here. So these were long thought to be related to the extinction, because people knew they were pretty much more or less the same time. But in fact, now we know that they are the exact same time. So the Siberian Traps occurred at exactly the same time as the carbon isotope shift and the mass extinction. This has been a relatively recent discovery, because it's actually kind of hard to determine the age of this type of lava, these basalts, because they contain almost no zircon minerals. And zircons are normally the main source of the uranium that people would use to calculate an age for the rock. But after quite a lot of work, it's now known that most of the lava for the Siberian Traps, many millions of cubic kilometers of lava, erupted over roughly a 250,000 year period between about 252.2 and 251.9 million years ago, and likely peaking with especially large and especially fast eruptions that would have released a lot of carbon dioxide very quickly during the carbon isotope excursion and the extinction itself. So what were the three? So how were these three environmental changes linked to the carbon release? Well, let's start with ocean acidification during the extinction. So at a broad scale, the cause here is quite straightforward. Carbon dioxide dissolves into water to form something called carbonic acid, which then makes the water more acidic. The nuances of ocean carbon chemistry are, yes, they're more complicated, but for our purposes, the overall picture is quite clear. When carbon dioxide is added very quickly to the atmosphere and then to the ocean pH decreases and it becomes more acidic. That happened from boron isotopes. That we can tell that happened during the Permian extinction. It's also what's happening to oceans today. We have good measurements today. Okay, so how about increased temperature during the Permian extinction? Well, this one's also very straightforward, at least at the general level. Increased carbon dioxide traps more energy in the atmosphere, and then the Earth's surface and the oceans both heat up. The physics behind this has been known for really more than a century. So, the greenhouse effect, as it's called, or global warming, is very clear. So this means that the carbon release, adding carbon, will simultaneously go into the ocean to cause ocean acidification and go into the atmosphere to cause warming of the Earth's surface and ocean. Okay, so finally, how about expansion of low oxygen areas in the ocean? Well, this one does require a little bit more discussion because it's kind of a chain of events. There's more factors that go into it. Okay, so the surface part of the ocean is in balance with the atmosphere, and oxygen can exchange between the two. Also, important nutrients such as nitrogen or phosphorus are supplied largely from the breakdown of rocks on the continents, and then via rivers they make their way into the ocean. So organisms in the surface ocean, algae and bacteria, will use sunlight and will use those nutrient elements to photosynthesize, which produces oxygen. So the surface ocean typically has lots of oxygen in it. These photosynthetic organisms also produce organic matter. Now, some of that organic matter is broken down or eaten in the surface ocean, and the organisms that do those things are also breathing in oxygen to do that. So that's called respiration. So some of the oxygen produced in the surface ocean is also consumed or used up in the surface ocean. But some of the organic matter from the algae and so forth sinks deeper into the ocean before it breaks down. And in fact, it's broken down or respired, as it's called, as it's sinking down into the deeper ocean. So that's actually using up oxygen in the deeper part of the ocean, but no oxygen is being produced down here, right? So there's oxygen being produced in the surface ocean, also some being consumed up there, oxygen being produced in the deeper ocean, or being consumed in the deeper ocean, but nothing produced down there. So the ocean water also physically moves around, kind of like a large sort of conveyor belt, where the water will sink in certain places, bringing oxygen down with it. It flows throughout the deep ocean, where the oxygen gets used up by that respiration by organisms, and then the low oxygen water will come back up to the surface in other places. So the fact that oxygen is used up to break down the sinking organic material, combined with the sort of the upwelling of lower oxygen deep water in certain places, contributes to something called an oxygen minimum zone, which is normally at sort of medium water depths, not in the surface ocean. Okay, so during something like the Permian Extinction, if we release a lot of carbon dioxide into the atmosphere, what does that do? How can we make these low oxygen areas expand? Well, it's in a number of ways. First, warmer water doesn't contain as much oxygen. So the warming of the ocean leads to lower oxygen values in the surface ocean in general. Next, a warmer climate will cause more breakdown of the rocks on land, or weathering as it's called, which will provide more nutrients to the ocean. So more nutrients cause more photosynthesis, and therefore more organic matter that sinks into the deeper parts of the ocean. Now, there's a more organic matter sinking. That means there's a greater amount of respiration in the deep ocean. Even more oxygen gets used up than before with this change. So again, we have overall there's less oxygen due to the warmer temperatures in the ocean, and more consumption of oxygen from this sinking organic matter, and that is what causes these oxygen minimum zones to expand, even, it looks like in the Permian Extinction, expanding into certain shallow ocean areas, even up into areas where the sunlight is reaching, and these are areas where lots of animals or other organisms would live. So in fact, this is what we're seeing today as well. Due to ocean warming and also nutrients from fertilizer being brought to the ocean, today the ocean is gradually losing oxygen, and these low oxygen dead zones are also expanding into shallow water. But back to the Permian. So, in the Permian Extinction and in many of these ancient episodes of rapid warming, which are called hyperthermals, we have a pretty consistent pattern of events throughout many of these particular episodes. So as I said, the Permian Extinction is one case, but there are other hyperthermals, and in many cases, they often cause extinctions that can be quite large or medium-sized extinctions. So what we have is the flood basalt eruption releases carbon dioxide quite rapidly, perhaps also releasing extra carbon dioxide if the lavas come up through coal deposits, as seems to have been the case for the Siberian Traps. The carbon dioxide causes the ocean and the atmosphere to get warmer, causes the ocean to get more acidic. The warmer climate leads to increased weathering or breakdown of rocks on land, which supplies more nutrients to the ocean, leading to an explosion in photosynthetic algae. And when they sink, Coupled with the warmer waters containing less oxygen, the oxygen minimum zones expand into shallow areas. So as I said, this chain of events is quite consistent at all of these ancient hyperthermals. It's also the chain of events that we're seeing in the oceans today, thanks to climate change. So we can actually learn quite a lot by comparing all these different events, both past and present. So that's it for today, and thanks for listening.